chapter. This is our last class today, and I'm gonna go over some topics with you. You guys, I'm gonna give you the basic foundation of these topics, and then you guys will have to basically, go and read in depth. So we stopped here in the last class, and somebody typed something. Okay, sorry. So we stopped here at the NAT. And what NAT means? NAT means network address translation. So what this means is because we have a concern for IPv4 addressing running out, we have like around 4.5 billion IP addresses. And the thing is, if we have 4.5 billion IP addresses, then we are running out because internet is expanding. We have got people from all over the world getting on the internet, so we are running out of IP addresses. So what they have done in the meanwhile, while IPv6 is getting pushed out, they're using private and public IP addresses. So anything which is private, which is within your home, is basically all private. But as soon as you go out on the internet, it basically becomes a public IP address. It gets converted into a public IP addresses. Okay, so this is the range 10.0.0.0/8, 172.16/12, and 192.168.0.0.16. And this is the complete range. I mean, this is from 10.0.0 to 10.255.255. If you find any of this IP address, which means this is a private IP address. These IP address is not going to go on the internet. You will not be allowed to go on the internet. So if I give you an example, if I do this IP config space /all, if you look at my IP address 10.0.0.1, this falls under, sorry, this is my IP address, my apologies, 10.0.0.93. This falls in this range, am I right? 10.0.0.93. So which means that this is my private IP address, but I'm not allowed to go on the internet with this IP address because on the ISPs, what they have specifically configured is any person comes in with a private IP address, do not let them go on the internet. So all these IP addresses get converted to a public IP address, and we all have public IP address. You will not be able to see it, but remember I told you if you guys go on the what do you call it? Internet speed test. So if I go here and I do internet speed test and I do the first one, Okla, and look at this. This is the IP address basically I'm getting converted to, right? So all my home IP addresses are from 10.0.0.1 to 10.0.0.254, sorry. And all of them are getting converted to this IP address from Rogers. This is my public. This is my one which is facing the internet. But as soon as it comes back, then it knows that there is a mapping that it's going to get converted from there to the one I have 10.0.0.93, which is my own IP address right here. So let's see how it basically gets changed, right? So private addresses are used within an organization to allow devices to communicate locally. However, private IP addresses can't be routed over the internet. This is exactly what I just said earlier. You will not be allowed to go on the internet having this 10.0.0 range, 10.0.0 to 10.255.255, or 172.16 to all the way to 172.31.255. All these ranges are not allowed to go on the internet. So what happens if you're not allowed to go on the internet? Then what happens is your private IP address gets converted to a public IP address. So I just showed you that mine was what, 99 dot something from Rogers. So all my 254 IP address will get converted to one IP address, which is a public. And the router basically keeps track of those and says, okay, if my address on this PC is 10.0.0.93, and if I'm going on the internet, I'll be taking that IP address. And as soon as I come back, is going to say, okay, you know what? I have basically mapped this 10.0.0.93 to this 99 dot, 0, whatever that dot x dot x dot x. So it keeps a track of where which IP from which private IP to which public IP it is converting to. So when the traffic comes back from the internet, it is gonna be by looking the router is gonna be looking at it and it's gonna convert it back to the private IP address. So that's what they're saying. NAT swaps the private IP source for the public IP address, right? So basically, the advantage is conserve legally registered addresses because we have got only 4.5 billion IP private public IP address, and it's not enough for the whole world, right? Because China is big on the internet. Africa is coming big on the internet. North America, Europe is already on the internet, right? So because of this, the scarcity of IPv4 addressing, we have to use this NAT, which is public to private conversion, and it hides IP address inside the network because you're not going out as which mine is 10.0.0.93. So it's basically hiding my IP address. It's not telling the world what my real IP address is. It's just using that whatever I just showed you on the speed test Okla, that this 99.x.x.x. So the world is seeing that 99, but it's not seeing that what is my currently configured 10.0.0.93, right? So let's just look at this, how this, just remember this and this logic, and that's about it. You can go in detail later on, but just remember this. Inside local SA is only, look, this is source, destination, source and destination address, right? That's what SA and DA means. Inside local means my inside local private IP address. My outside local is basically what I'm trying to go to. Inside global is what this inside local, my private IP address, has been converted to. So remember this, guys, just drill it in your heads. Inside local is your private, and inside global, easy way to remember. Inside local means inside your network. Inside global means inside address for the global is 209. So this basically is mapping 192.168.10.10 gets converted to 209.165.200.226. Understood? Outside local and outside global exactly the same is because I'm going to the internet. I'm not going to be seeing any of this private IP or whatever that is, right? So understand inside local and inside global is private to public, and then outside local or outside global is basically I'm going outside of my network. I'm going on the internet. So that will already is going to be a public IP address. Static address translation, dynamic address translation, and port address translation. Static is one-to-one. If I've got a 20 private IP address, then I'll be converting into them 20 public IP address. That's what static address translation means. But this is horrible because I mean, if I've got 40, 50 users and all of them are going to the internet, you think I will get 20 or 40 or 50 public address? Absolutely not, right? So this is basically in the beginning, they were coming up with this one-to-one. Dynamic is, let's suppose they have got 10 addresses and they have got 60 or 80 or 90 private IP address. So whoever goes first on the internet, they're going to take that one IP address. Second one's going to take the second one, third one, fourth one, fifth one, till all the way to down to 10 public IP address. But the problem is, if you have got 40, 50 users sitting, the first 10 gets it, and what the rest are going to do, right? So this is a problem. In the beginning, it was fine, but now it's a problem. So that's why they came with many to one address mapping between local and global address. This method is also known as overloading, not overloading. So we're going to see what this is. What they're saying is a lot of IP addresses can get converted to only one public IP address, right? And this is port based. So we're going to see how this is. I'm going to explain this, how this is written. IPNAT inside source static 192.168.10.254 converted to 209.165.201.5. So they're saying IPNAT inside means my inside local client IP address statically map this IP, because this is a private IP, and convert it to this public IP address. IPNAT inside and IPNAT outside. What they're saying is serial 00 R2 serial 00 is basically they're saying inside, this is my inside network. And outside is serial 010, which is facing the internet. Serial 00 is my local, my inside network, and serial 010 is outside. So that's why they're saying IPNAT inside. This is my inside conversion. And when you go out, basically you're going to be going out through serial 010. Understood, guys? How many people are there at this time? Okay, we still got four. Now, what did this is the second option. Remember, I was showing you the second option. There is one-to-one, which is this is what one-to-one is, and this is IPNAT pool because this is a pool access list. You can put any name you want. 209.165.200.226 to 240. So this has got basically 14 IP address. Net mask, this is 255.255.225.224. So they're saying I'm going to create a pool, I'll access this pool of these 14 public IP address. And then what I'm going to say, access list 1, permit 192.160.0.0/24. Imagine how many IP addresses are going to be here. It's going to be like around, I think if I'm not mistaken, it's going to be like around 512 IP addresses. So 512 IP addresses are going to be only assigned 14 addresses. So if you have got 500 PCs sitting and you only 14 are basically going to be able to go out, on the 15 one, that's it, you're done. You're not going to be able to go out and connect on the internet. So this is also a horrible example, but in the beginning it was fine, right? But this is the one which we use nowadays. IP NAT pool, NAT pool 2, 209.165.200.226, 240, prefix length 27. 27 is the same thing as 255.255.255.20 Permit 192.168.0016. And then IP inside source list 1, NAT pool 2, because this is the name of the NAT pool, you can put anything you want. Overload. What this overload is, it uses the port numbers. By having this overload, it uses the port numbers. IPNAT inside, which is this one, and IPNAT outside is basically you're the one which is interface, which is facing the world. So overload, IPNAT inside, access list 1, 0010, overload. So basically you're saying that make sure you use the port numbers. Understood, guys? DHCP. This is Dynamic Host Configuration Protocol. What this does, it says there are three ways you do it. Statically, the manual. Dynamically, basically the DHCP automatically assigns an IP address from the pool, and automatic static allocation. DHCP automatically assigns a static IP address permanently to a device selecting from a pool of available addresses. This is what it is. This is what it is. Every PC needs to have an IP address, right? If you have an IP address, then basically you will be able to communicate with the outside world. If you don't have it, then you will not be able to communicate. So you manually giving IP address to the every single PC. Dynamically allocation is the DHCP server is basically allocating you, right? And when we used to manage the DHCP, what we used to do, let's suppose if I have a 254 IP address allocated to us from the DHCP, the first 50 or first 30, we will block it out. Do not assign it to anybody. Those the one we have blocked in the DHCP server is the reason we block it is so that we can give it to the printer, we can give it to the server, we can give it to the router, we can give it to the switch. Anything, the network devices, we can give it because we don't want the network devices to keep getting new IP addresses. So how this communication works, basically the client, it sends a broadcast, DHCP broadcast. Then it goes to the server. Server replies back and it basically gives you an IP address. It gives you an IP address, it gives you a subnet mask, it gives you the default gateway in the DNS information. And then what happened is the client receives it and he basically says, okay, I'll accept it. He sends an acknowledgement back. And basically the DHCP server sends, for how long, because it all depends how long you want to keep those IP addresses. Do you want to keep it for 7 days, for 3 days, or for 10 days, right? Everybody's configuration is different. Everybody policy in company is different. So it all depends on that. So this is exactly what we're just showing you here. So this is another way of looking at it. So the DHCP in the enterprises, you will probably have one DHCP server here, and then all these devices are going to be trying to get a DHCP server from IP address from here, right? You might have a DHCP in the big environment. You might have one primary DHCP and the other one is a secondary DHCP, and they both are basically syncing in the background in order to make sure that nothing gets overlooked, nothing gets overlapped. So basically if the primary goes down, then the secondary basically takes over. So in a big environment you need to have basically a primary and a secondary servers, right? So this, if you want to configure it on the router, you can do it also. All they're doing is IP ADHCP exclude address 10.1 to 10.9 and 10.254. What this is exactly what we used to do on the DHCP server itself. What we do on the DHCP server, we say, you know what, block these IP addresses. So that's exactly what they're saying. We are excluding these addresses from getting allocated to any of the PCs which are requesting for an IP address, and we create a DHCP pool, like whatever this LAN pool 10 is basically, is just an example. You can put any name you want, right? Network is 10.0/24. So this is what you can, your range can have 192.168.10.1 to 192.168.10.254. So you can have 254 IP addresses, but out of those 254 IP addresses, you're basically blocking away 10 IP addresses from 10.1. If it's in the sequence, then it's fine. Then we can basically write it like this, which means from 10.1 to 10.9. And this is 10.254. So basically you have to, because this is not in the sequence, so you have to put a second line here. Understood? And default router, this is basically saying, what is the default router? The gateway router. This is your default router, the point. Any PC which wants to go out, it has to send information to the default router. Same thing here for 11. Same thing they're showing you here. So if a DHCP server is sitting here, and this guy, PC1, wants to get an IP address, all he has to do is basically send a broadcast. And then the router is basically always the one which blocks the broadcast, right? So you have to use the IP helper address here in order to define what is the DHCP server IP address. So any DHCP basically broadcast comes in from the PCs, it is simply going to be sending it to the DHCP server over here. Otherwise, the role of a DHCP is basically to assign IP address, and the role of a layer 3 device is any broadcast, no matter if it's for DHCP or for anything else, you have to make sure you disable it, right? So layer 3 always disables the broadcast, but in order to avoid that, we have to put an IP helper address. And so basically you're telling a layer 3 device that, my friend, if any traffic comes in for the DHCP, make sure you don't block it, you just you forward it to the DHCP server. This is the IP helper address I was telling you about. So basically on FAS00, you're going to say any broadcast comes in for DHCP, simply forward it to this guy 11.5. Understood? Otherwise, if you don't have this, what will happen? Your PC1 broadcast comes in. By default, the 3 device will disable it. It's not going to accept it. So because of this, he's going to forward the broadcast out, right? Any IP address DHCP basically, enables Cisco device to obtain an IP address dynamically from the DHCP server. So this is, if you want to get an IP address from an ISP, just do IP address DHCP. So this ISP is going to give you the IP address on this interface. This is what it means. This so these are basically very huge topics, but the thing is that I'm giving you an understanding of these topics that if you want to go in more detail, you can go in more detail on it, right? And just like this one, spanning tree, I'm not going to be covering too much of this because spanning tree itself, if you go and look on the internet, you're going to find book for 200 and 250 pages. Just this topic is basically got 200 pages book. So let's look at what spanning tree does. STP, spanning tree protocol.
Say, Imtiaz,
Yes, sir.
yeah, before you go forward, I have a couple of questions for you.
Yes, sir.
I have noticed when I have a router at home, when the internet connection from outside it goes away, so I can't from internal side I cannot have access to the router. Why is that? I mean, why is happening? The
Um,
second is, yeah,
please go ahead.
and the second question is sometimes I realize when the router is kick you out from the network, you can't go back. Even you reset the NIC card, you don't get unless you reset the router. Then you can sit back again in the network. So why the router is acting like this?
This is your Rogers or Bell router, right?
Well, you have only three big networks. It doesn't matter you sitting in Rogers or any Rogers, it's
That's
acting the
what I
same
have
thing.
to do. That's what I have to do every month. Every month after 20, 25 days, I have to reboot my router at home. Unplug it, 15, 20 seconds, put it back in. The problem is on this line, I don't know what the speed is on your line, what the bandwidth is, but what happens is you're using a TV, you're having a voice chat and videos, you're watching YouTube, you're watching movies and everything. So basically what happens is a lot of traffic piles up on it, right? Sometimes there are issues with the network on the Rogers end also, right? So basically because of all that, and let's suppose you were watching YouTube or something, right? As per the router, it should clear out when if you're not connected, but it stores the information on the system on the router itself. So that's why we have to reboot these routers. These routers are not the one you use in the production environment for a company. This is just for the internet connectivity.
No, I know that, but I mean, I don't understand the logic because the first question is uh, when what was my question first? Oh God. Uh, what was that? My question. Yeah, let's focus on the second question until I remember the first one. My second question is when it drop you out from the network, you never get back until you reset the router. So otherwise, it doesn't let you sit in here. So that's a
Because
strange because I don't understand the logic behind this router. I mean, is the application or the software of this? What is it?
it
Why
must be
it
the
doesn't let you
box.
set it back?
It must be your box. Because when my Roger kicks me out, my internet goes down and then it gets restored. I can go to the internet without, doing anything. So if you have to reboot it, then basically something issue, there is an issue with your router from the ISP itself.
Well, actually, I have been in a couple of different ISP. The same situation is happening, and the worst is the Rogers because Rogers has a problem with the cables and they have lots of noise and they don't want to accept and take this initiative to make something because I have a lots of cost for them to 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 fix this noise in their cables. Because I tried a couple of weeks ago, I had issues with the router. Well, actually, the router has two issues. First, was not advertising through the wireless. That was clearly was problems, hardware problems. But the other problem is, or still is, that when I'm checking the log file in the router, I can see there are lots of errors coming, and I connected the router to the cable exact from outside, I mean from the basement. So I didn't want to have excuses from the ISP that you have a problem inside the house. So I excluded that, but they didn't want to accept it because they were mentioning that you have to watch the LED lights on the router to see if there is something wrong with these lights, and then you can take a photo
No, no,
and
no.
return it back. That's
That
so
that's
stupid
complete.
nonsense I got
That's
from them.
it's that's complete BS. It shouldn't be
Mm.
that. Even though you have the lights on, that doesn't mean that you're not getting errors. Even if you're getting errors, you have all the lights on. You will have all the lights on. If there is a lot of
But
distortion
let
on
me
the
just interrupt you, people here. I think Wahid, we can discuss this later. This is a specific issue for you only. Let us focus on the class for that purpose,
Mm.
and we will discuss about
Mm.
this, inshallah. Okay, Wahid.
Okay.
Yeah, thank you.
so Bhai, the problem for you is basically your router itself. So you got to call Rogers and have them replace it. That's all I can tell you. So redundancy at OSI layer 1 and layer 2. So this STP is basically spanning tree protocol. This is a layer 2. What it simply does, it says if I have two ways to get to the destination, I am going to disable one path and I'm going to leave one path up and I'm going to start routing from there. And I'm once if this path goes down, then I'm going to automatically enable the other path and I'm going to start routing the packet or start sending the packet through the other path, right? So the only reason they're doing it in STP is basically if you have two redundant paths to get to the destination, then basically there is always a problem of getting a loop created, right? Because the other end, you're getting information from this end that, hey, I know how to get to this. Then also from the second end, from the second path, also telling the other router, hey, I can also know how to get to it. So basically, there is always a chance in the layer two environment to create a loop. So in order to avoid this layer two loop issue, this STP was introduced. So this example over here, if the layer one is basically what happens. If you look at this, an STP works on basically your layer two switches. So you got a switch one, switch one, switch two, and switch three. Now this PC can either go from here to here, go from here to here, and here to here. Now what this guy is going to be saying that in order to get to this PC, you can simply come to me. I know how to get to it. I'll just simply send the traffic from here to here. But S3 is also telling S2, hey, I also know how to get to the PC2, right? So this can create a loop. So in order to avoid this loop, let's suppose there are two trunks here, trunk one, trunk two, and trunk three. So all it does, it says, I'm going to disable my trunk one and I'm going to take this path from S2 to S3 and S3 to S1. If this link goes down, trunk two goes down, then I'm going to enable my trunk one and I'm going to start sending the packet. Otherwise, there is going to be a loop situation in this. So in order to avoid that, basically what STP does, it blocks one redundant path and takes this traffic and sends the traffic from the other end. So that's what they're showing you here. So this is exactly what it is, what I was explaining to you. That there, everybody is going to be telling everybody, hey, I know how to get to this 172.17.10.22. When in actuality, so this guy sends traffic to him, he sends to him, this guy sends to him, and this is a loop created. A loop can get created. So basically, an unknown unicast frame is when the switch does not have the destination MAC headers in the MAC table and had to broadcast their frame out to all ports except the port that frame was received, right? So basically, if the frame, what switch does, if he doesn't know how to get to this destination, and then what happened, he's not going to be sending out or sending it out to other switches from the same port it has received that information. Ingress is when the packets come in. egress when the packets go out, right? So he's going to be sending out to everybody, and then everybody is going to be basically receiving it. So he says, I know it. He says, I know it. And he says, I don't know how to get to it. So she's going to be sending it to him. He's going to be sending it to him. He's going to be sending it to him. S3 will send it to S1. So this is a problem right there. So this is, redundant design because every switch is connected to every other switch for redundancy purposes, right? If one link goes down, then at least you have a path to get to the destination wherever you're going to go to. In any work environment, in any corporate environment, you will always see switches have two connections out there. You will never have like one connection. Let me take my words back. I have seen one connections also, but the thing is that most of the time I've seen there's always a redundant connectivity for the switches. And the only reason you do a redundancy is making sure if one link fails, then the other link basically is up. So the spanning tree, what it does, creates one logical path through the switch. This is what we were saying. Blocks redundant path that could cause a loop. So basically, if you have trunk 1, trunk 2, and trunk 3, so it basically blocks this path, right? Or it can block this path. So it can block any path. And then once basically this connection goes down, the protocol is smart enough to say, okay, this is basically, the connection is lost. So let me enable this path right here. So if this is down, then what happened? This comes up, then either you can go this way, or if you want to go to S3, then you can go from S2 to S1 and S1 to S3. There's something called port roles. What happened? There is an election happen, and this election, what they're saying is anything which is basically there's something election happened in Spanish tree and it says the root bridge. Root bridge is the bridge is basically is kind of primary switch. Any information you send the information to the root bridge, you don't send it to any other switches. And root bridge becomes a primary. What in our networks, what we have done is basically we select the root bridge. Otherwise, if you don't select the root bridge, the spanning tree protocol would automatically select it for you. So we select the switch which has got less connectivity on it, so that in order to avoid a lot of processor and CPU and memory spikes, right? So basically, root path cost is used to determine the role of the port and whether the not traffic is blocked or not. So basically what happens, you can simply use the cost mechanism in order to make sure that which port or which switch you want to make it a root bridge, because we want to control our selection of the switch to be the root bridge or a designated switch. Root bridge is basically the one which basically in this way, and designated is basically the backup switches. So this is just to showing you, in order to create the bridge IDs and root IDs, what it does, it basically adds your MAC address and also basically adds the number of VLANs configured on the switch. Path cost is basically determining basically whether it's a GigE connection, whether it's a fast E connection, or it's an Ethernet connection. So the higher the bandwidth, the lower the cost. Understood? So basically, if you have got a 1 gig, it basically gonna be like around 5 or 1. If you got a fast Ethernet, it will be like 19. So basically, it all depends what the path cost is and what the connectivity is. And you can also go in and manually change it. And we basically very frequently used to do it. And the reason we used to do it is basically we want to do the selection ourselves rather than making STP deciding how we basically wanted to make, which one we want to make the root bridge and the designated backup switch. So that's what they're saying here. So this is the root bridge. These are the designated root ports. Anything facing to the root bridge becomes a root port. Anything facing basically from the designated port are the only those ports which has the root bridge on top of it. If I'm the root bridge, I'll have the designated port going out to the other switches. And my all other switches will become facing the root bridge will become the root port. So that's what they are. From here, root port, designated port, because you see this is not facing, not going towards the S1. So S2 going to the root bridge. This is also going to the root bridge. They all becomes the root port. Anything which is going towards the root bridge will become the root port. Anything which goes from the root bridge outside to the other switches will become the designated port. That's what the role is.
Mr. Imtiaz, why shouldn't we use router in between instead for connecting so many
This
switches
is
together?
this is for layer two, my friend.
Yeah,
If
I
you
know,
have
but I mean, I think in previous classes you were mentioning we have a router and then we have the switches and you have to go outside. But here maybe we don't have to go outside, but still, if you want to avoid STP, then we can use the router instead for connecting so many switches together.
you see what
Can we
happens,
do that?
it all depends how you want to design it. If you have got people sitting on two, three
Hello,
floor, hello, can you hear me? Can you guys hear me?
I can hear you now. Yeah.
Yeah. What I'm saying is every design is different, right? If you have two or three floors and you have got two, three switches on each floor, right? And then you are basically on the first floor, you have got two routers sitting, and all these ports are coming to those two routers. But you have got all these two, three, four, five switches interconnected with each other, right? Because they are in different VLANs and everything.
Mm.
Understood?
Yeah.
It all depends how you want to design it, my friend. It all depends on that. Okay.
Okay.
But if you have a design where there, like you have got five switches and they're interconnected with each other, then you are going to be using STP. But if you have got only two switches connecting together and then going to the router, obviously you're not going to be using STP there. So it all depends. If you have a bigger environment, then you have to use STP because there is always a danger of a loop creation there. So it all depends how you design it. This is exactly showing you what we were just talking about it. Same example, what we just talked, right? So this, as I said before, so these are basically, if priorities are all set to the default, the lowest MAC address is determining the factor in lowest BID. The priority value can be modified to influence the root bridge elections. That's what I said earlier. What they have here. So basically, you have to manipulate the priority on the switch in order to make sure that it's the one which gets selected as the root bridge. We do never let the switches decide on themselves to see who the root bridges is. So that's what they're mentioning here, exactly what I was mentioning. So these are basically different. 1998, it was 82.1D. Then, later on, they kept on changing. In 2004, 82.1D was introduced. RSTP was introduced. PVST, this is PVST means per VLAN spanning tree plus. Multiple VLANs can have the same spanning tree instances. MSTP. A lot of people use basically PVST plus or also RSTP. What this does is basically in this feature, what is happening and why they keep on improving on these protocols is because we are using voice and video in our network, right? If you have these three, four switches connected together and one link goes down and the other one comes up, it basically comes up in stages. listening, learning, and then forwarding state. Your voice does not have time for doing all this listening, learning, and forwarding. So basically, because of the voice technology, it goes from the blocking directly and bypassing the listening and learning to forwarding. That's why the voice is using a UDP, and UDP is 8 byte, and your TCP is 21 bytes, right? So that's why the programmers, they use UDP for the voice technology, because you don't want all this 21 byte, in your voice technology. You don't want the lesser and lesser delay you want for this voice. So that's why the new improved spanning tree was introduced, because of this voice and video and all the video conference is making sure that if the port is in blocking state, it doesn't go into the listening and learning and forwarding state. It just jumps directly from the blocking to the forwarding state. So STP, PVST per VLAN basis, all VLAN bases, right? So basically, these are the characteristics of spanning tree protocols. What I've given you is basically the basics of spanning tree protocol. Trust me, go on Google and check the STP. If you call Cisco or if you call Juniper, you're going to find people sitting in this company for support only for STP. That's it, and they're not doing anything else. So this is such a huge, basically, protocol. So overview of PVST plus is basically one spanning tree instances for the switch network, no matter how many VLANs. No load sharing. One uplink must block all VLANs. So basically, what they're saying is one must block, and the other one should keep on going forwarding the VLANs. Or if you want, you can block it for per VLAN basis. Let's suppose you're saying block it for 10, but forward 20. That's the example here. On the other link, block 20, forward 10. So you're basically balancing your act, you're balancing your path. So you're saying send only VLAN 10 from here, send VLAN 20 from here, you know, and the block of the VLANs. That's exactly what they're saying. Blocking, listening, learning, forwarding state, right? So the extended system ID field ensures that the switch has a unique BID, bridge ID. This is the bridge ID. VLAN 2, remember, the default value is 32,768. And every time the VLAN number gets added, VLAN 2 or VLAN 4, if it's VLAN 2, then this 7268, 32768 becomes 3276, sorry, 32770. If VLAN number 10 gets added, then it will become basically 32778. So anytime the VLAN number gets added, it adds on that value itself on the bridge ID. Can modify the priority number or to influence the root bridge decision. Reasons to select a particular switch was the root. Switch is positioned such that most traffic patterns flow towards this particular switch. Switch has more processing power. That's what I'm saying. In our networks, how we select, we want to make sure that one switch does not have too much load on it, not too much servers connected, not too much PCs connected. And we said, okay, fine. Now we're going to use this switch as a root bridge. So root bridge, what happens? It basically gets traffic from all other switches for not the real data traffic, but the protocol. Hey, I am up. Hey, this is the one sending hello, getting a reply back and everything. So basically, that's what the root bridge is for. It doesn't want, it just wants to handle all these hellos, all these connectivity issues and everything. The root bridge wants to just monitor the whole network, right? So we always select in our networks, we have always selected the switch, which has got a lot of CPU power and a lot of memory power. So this is a rapid PVST. Rapid PVST means that you're bypassing some basically sequence. So as I said earlier, from blocking, you go directly to forwarding, right? Because you're not going from blocking to listening to learning and then forwarding. So you're bypassing those two basically flows in between. And that's why it's called rapid, that you're jumping from blocking to forwarding all of a sudden. And there is a configuration basically you configure on the interface itself to make sure that it bypasses those two. And because of any time when you have the voice connection over here on the switches, we make sure that this goes from directly from blocking to forwarding. Edge ports are always those ports which where the PCs are getting connected on the switch, right? Those are the edge ports. So this is if you go on the Google or you go on the Cisco, you have to basically define the type of switch you have, and it will give you what's the default configuration for it. Every switch is a little different. This I've just put it in for 2960s, but you can go on Google and you can go on Cisco website, whatever your model is for the device, you can simply go and look at default configuration, what it can handle, what is this capable of, right? All this for every series. You got 2960, 3550s, 4500, 5000 series, 6000 series, 7000, you got 12,000 series. There are so many series out there, right? And all these series have a little bit different capabilities. So that's what, I've just put 2960 here. If you wanted to find out more of the switches you have, go on their website. Okay. So this is just to show you that, spanning tree pore fast is this is the one I was telling you, that where it says I'm bypassing those two layers of listening and learning, and I want to just enable it for my voice connectivity. I'm enabling it from my blocking to the forwarding. So basically, you always have to make sure that you put spanning tree pore fast, and spanning tree pore fast is basically always gets configured on these interfaces if you have any voice connectivity ports, voice over IP phones, right? Because voice over IP phones are what? You got a voice over IP phone cable going into the switch port, and then on your basically PC going from the cable going from your PC and into the IP phone itself, right? So that's why you need to make sure the spanning tree port fast is there. This is saying spanning tree configuration. This is the same example I was explaining you earlier. On the switch tree, spanning tree VLAN 20 root primary, spanning tree VLAN 10 root secondary. What this is saying that for switch tree, I am the primary switch. I'm the root bridge for my VLAN number 20, and 10 is the backup. On switch 2 or switch 1, this one, I'm saying I am the root bridge basically for VLAN 10. I'm giving it a priority. And my secondary is basically the VLAN 20 on S1, right? So you have to go and read a lot in this. Uh, the other chapter is Ether channel, HSRP. Ether channel is what? It's simple. Ether channel is, you're going to see this a lot of places. Ether channel, you got basically, what do you call it, bundle IDs. You got AE zeros, AE ones, depending on the vendor. If I talk about Cisco, if I talk about Juniper, Arista, Ciena, white boxes, all these different vendors, they are either using Ether channels or they're using the bundle IDs. Bundle IDs is basically for the layer 3. Ether channel is basically for your layer 2. What this simply does, just drill it in your heads. What this simply does, it takes, if let's suppose this is 1 gig connection, this is 2 gig connection. Physically, this becomes both of them. So basically 1 gig and 1 gig becomes 2 gig. So in reality, you have got two cables connected on 1 gig and 1 gig, but the devices are going to see it as a 2 gig. So your total speed becomes 2 gigs. So basically you create a bundle, and in that bundle, you combine these two cables together and say, well, I've got, instead of 1 gig, I've got 2 gigs. So basically, this is virtually combining these devices, these links, physical links, into one virtual link. Physically, there are two, virtually, there's one. So let me explain this here. I put in an example here, and then I'm going to go back and just understand this configuration, and then the rest of the stuff is going to be very easy. How do we configure it? Interface, range, fast Ethernet 01 and 02. Range is what? Ranges means in a sequence. If I'm taking fast 01, fast Ethernet 02, fast Ethernet 03, I'm going to be saying interface range, fast Ethernet 01 dash 3, which means from port 1 to port 3, I'm going to make it a channel group 1 mode active, which means I'm going to make a channel group. Channel group, you can put 1, you can put 2, you can put 3, whatever number you want to put, you can put it in. This is just a number that they have selected. Then you say port channel. So basically, it will create a port channel for you. You create a 1 port channel group 1, and all you do, you basically interface port channel. You're going under an interface now of the port channel itself. Switchboard mode trunk, switchboard trunk allow, VLAN 1, 2, and 20. So let me explain this. If we understand this, then the 2, 3 pages I skipped before, you will understand that. All they're showing you here is you're creating this range. Under this range of fast 1 and 2, you're creating a port channel group 1, simple, and making it active. And then you are basically going under an interface port channel itself here. And you're saying this is a trunk port. This is basically VLAN for VLAN 1 and 2 and 20. Allow VLAN 1, 2, and 20. So this is, instead of putting a trunk here and here, there we have basically put it under a port channel itself. Understood, guys? So what they are saying here is not formed because you both have to have the same duplex and same VLAN number or same speed. You cannot have half duplex here and full duplex there. Duplex is what? Send and receive at the same time. Half duplex is what? It will send, and once it's done, then it's be able to receive it, right? So this is basically the best format to show you. It's gonna basically form. It's gonna basically form once the speed and the duplex is exactly the same. So this is just showing you the configuration. I've given you all the labs and everything for this. All the commands and everything. So this is just the same thing from the lab. You have to do this lab in order to understand this. So basically, when you're troubleshooting, you have to make sure that you have to check the speed on both ends. You have to check the duplex on both ends. Native and allowed VLANs on trunk ports, what VLANs you can allow to go on the trunk port itself, or if you put a switch for more trunk, it will take traffic from all the VLANs, right? It will take traffic from all the VLANs. But if you say here, what we said here, on this end right here, switchboard trunk allow VLAN 1 to 2 and 20, which means that you're gonna only allow these 3 VLANs to go across. Because I explained that the trunk ports are those ports whose job is to carry traffic from different VLANs. Okay, so this is, uh, forget about this, that, if one is active, other one is desirable, then the ether channel will get created. Nobody uses this feature. I'm not going to be able to remember in a production environment whether I should have a desirable on one end configured for my channel group and on or active on the other end. I will not remember. So basically, the best practice is keep it on both ends. I don't care about desirable or this is just a feature Cisco saying we have it. you know. But in production environment, you never use this combination of desirable or desirable. If both interfaces are desirable, then it will create an ether channel. So we don't care about it, tell you the truth. So that's why you have to make sure you put both on and on both interfaces on the ether channel. Then it will be basically active. Because who's going to remember all the tables? That's what they're saying. Desirable, and non-desirable. Now, this is HSRP. So HSRP is what? HSRP is basically hot standby routing protocol. This is a Cisco proprietary. What this simply does, it says, my friend, if you can have only one IP address for your default gateway for your PC, right? But what happens is, what if this router goes down? Then what happened? You're done. But what HSRP does, it says, if I'm your router one and I'm your router two, then this PC will have a basically default gateway, which will be configured over here and here for both. So one will take the primary role and the other one will take the secondary role. If this R1 goes out the window, then at least the PC1 will start going to R2, and then from R2 it will start be going up to the server. So the HSRP, there is a new IP address gets configured, and this is HSRP is Cisco proprietary. When you use Juniper, you use VRRP, right? And you use Arista, Sienna, and all these, they basically use VRRP. VRRP is basically for other vendors. Cisco has basically HSRP. So what happens, look at this. You have got one router, you got the other router. So one IP is 192.0.2.1, and the other router, standby router, is 192.0.2.2. Now you create a virtual router. This virtual router gets created on both the routers, layer 3 devices, and all the PCs default gateway will be 192.0.2.100. The higher basically the HSRP address, the priority address, it will be preferred. So R1 is basically your active. If your R1 goes down, if this router goes down, then he's going to take over. The reason this was introduced, because if PC1, PC2, 3, and 4 all are going to this router, what if this router crashes? What happens? Their default gateway is done. Their default gateway is down, right? Nothing can happen then. So that's why a new technology was introduced is HSRP, that even though this router goes down, then basically you need to configure an IP address on both the routers for this one. A new IP address gets created, and through this new IP address, all the PCs are going to be connecting to this new IP address, which is called HSRP. They will be configured on this one, and they will be configured on the standby router both, right? So this is the example. If this guy goes down, as I was saying earlier, then all the traffic is going to be routed through this guy to the ISP backbone. If we use a physical, if all these PCs use 192.0.2.1, and basically if this connection goes down, then nobody would be able to go out to the internet. So that's why a new IP address 192.0.200 is a 192.0.2.100 gets configured on this router and gets configured on this router, HSRP. So what happens if this goes down? These devices are smart enough to know that the primary is gone. I'm going to basically take the primary role, and then you all guys send the traffic to me, and I'll make sure that I take it to the final destination. Okay, so that's what this is they're talking about. So overview, one of the routers selected by the HSRP. So this is just a virtual, virtual router or virtual IP. That's a virtual router, it's a virtual IP. So all these guys are going to have 172.16.10.1, and it will be configured here and here, both. So one will be active, one will be the backup. We call preempt, right? So one, if this primary goes down, he's going to take over the role for all these PCs to send the traffic this way. So these are basically different versions: HSRP version 1, HSRP version 2. You can group as a group is 20 to 255. This is basically the multicast address. Virtual MAC address, this is the virtual MAC address already given. Whoever has programmed it, it's already given. So there is a lab for it too. I put it into the lab. You guys can practice it as much as you want. This you have to understand is basically HSRP priority and preemption. What priority is, by default, router with the numerically highest IP address is elected as an active router. So control, as I said earlier in an STP also, we don't want these protocols to be basically doing this selection themselves. We want to control how our path and which path we should be making a primary and the other one as secondary, right? So in order to do that, the routers are going to take the highest IP, whatever the highest IP address is. HSRP is going to say, okay, you know what? I'm going to become primary. We don't want that. If what this R1 has the highest IP address, or R2 has the highest IP address, then everybody is going. This is going to become the primary, and this is going to become the secondary. We don't want that. Basically, we want R1 to be the primary. So that's what we have to do. The default HSRP priority is 100. Range is 0 to 255, and the router with the highest priority will become the active one. And we have to change the priority on the HSRP. There's a whole configuration for it. We have to change the priority. And what we do in our networks, we change the priority to 110, right? And the other one, we just leave it the way it is because by default, the priority is 100. So the higher the priority, the active or the primary router that will become. So in our case, we on R1, when we are configuring the HSRP, we're going to make it as priority as 110, and we don't have to configure anything here because by default it's 100. The preempt they're talking about, we also configure preempt. What preempt does, if R1 goes out, right, goes down, comes, so basically R2 becomes the primary, right? Because R1 is out, it's down. When R1 recovers, then the election will happen again. So this preempt says, okay, my friend, I'm back again. Now I'll be the primary. Okay, so it will take the role back. So that's what they're saying. To force a new HSRP election process, preempt must be enabled on the standby router. So this is initial learning, listening, speaking, standby, and active. This is basically the role. If the primary goes down and the secondary is there, basically what happens is he's going to initialize, he's going to start learning, listening, speaking. It's a standby mode, and from the standby, it's going to basically becomes an active router. So it has to go through all these stages. So how do we configure it? Standby version 2, right? So let me what they're showing you here, I'm going to show you here. This is exactly what they're trying to tell you on this page. So what this is basically, look at this, R1 and R2, look at this configuration. Gig 01 is here, gig 01 is here. IP address 172.16.10.2, right? Standby version 2, standby version, this is version 2 is basically the latest. Standby 1, IP 10.1. This is a virtual IP you're creating. And look at the priority. Priority is 150. What is the default I said? The default is 100. Standby one, preempt. What this means is, what I said earlier, is once R1 goes down, R2 is going to take over and becomes the primary. But when the R1 recovers, what it will do, it will force the election to happen again, and because it wants to take the role back as a primary router. This is on the R2 configuration, IP address 10.3, standby version 2, standby 1, IP 172.16.10.1. So 10.1 is here, 10.1 is here. This is the default gateway for all these PCs. and no shutdown. Basically, just make sure that the interface comes up. So basically what happens is this is the default gateway for all these guys. But because it has a priority of 150, R1 is going to take the role as the Big Daddy, and this is going to be the backup router here. And preempt, as I said, is going to make sure that as soon as I recover, I'm going to make sure that the election happens. And I want to take back my role as a primary router. So this is just to show standby, which one is primary and which one is backup. This is basically in your lab. So you guys show standby brief. This is active role, standby role, so it's going to give you all that. So when you're doing the lab, you can look at it. HSRP failure, basically if this is, if you don't have a preempt, basically if it comes up, then the election will not happen till the second one goes down. Right? So you have to make sure you put the standards. The failing to remember when the control of the virtual IP of the group should be handed over to another. So, but what most issues will arise during one of the following: failing to successfully elect the active router, but we basically do it. We basically manually configure it to make sure who becomes the and what we do basically, we make sure which layer 3 device has got lesser load on it, higher CPU, higher memory on it, and then that's those by looking at those we decide, okay, is we're gonna pick this one to be the primary. And that's what we do with Juniper. That's what we do with Arista, and what we do with Sienna, and all these other network devices we do with. So these are all the debug commands. Debug commands is basically to troubleshoot the errors. What debug does, anytime you're sending and receiving any packets, basically the debug commands are going to be showing you all the outputs. In a production environment, it's a horrible idea to run the debug on the production routers. You can do it as much as you want in the lab environment, but never do it in the production, because you can bring the router down, because debug is going to give you every single traffic which is going across on the router, and it's going to show you on a term one on the console page right there. Right, so it's never a good idea to do it in the production environment. If you know exactly what specific debug you can run, but never run the whole debugs on your routers. But in your lab environment, yeah. Debug standby packets, basically sending and receiving. What is the primary? What is the primary via HSRP IP address, right? What are the hello? What is a dead interval? All that kind of stuff. So this is all your lab. You got to do practice on your lab environment. Configuration issues, HSRP routers are not connected to the same network. It could be also the VLAN sub-interfaces configuration issue. HSRP routers priority subnets are wrong. Your virtual IP address is configured wrong. It could be from a different network. You have to be in the same network in order to create those virtual IPs for your HSRP. And the group numbers, make sure that the group numbers are same. And devices not configured with the correct default gateways. If your PCs are not configured with the correct IP address, the default gateway for your the HSRP IP address or VRRP IP address, it will never work for you, right? So these are the configuration issues. Okay, that's it, guys. This is the last one I had. Any questions? Any question, guys? Can you explain Pat with the example slides? Oh, I'm sorry, Almas. Did I explain that, Almas, earlier? This is, Almas, what this is. Not overload is basically the port numbers. Inside local IP address is 10.10.10.10. This is your, if you go on Google and if you search the port numbers, you're going to find 1 to 65,535 port numbers out there, right? And what Windows operating system does is randomly picks the port number for the your device itself. So basically what happened inside global is basically what your private IP address gets converted to your public IP address. Outside global and outside local address is going to be the same, is basically why you're going on the internet itself. So what they're saying, this is your private IP with this source port number gets mapped to this 209.165.200.226 on this port number 1555, and it's going on to the destination server on port 80. Port 80 is what? HTTP. And at the same time, 10.11 is also mapping 1331. So when the traffic comes back in, what will happen? The router is smart enough because he has a table. And when he's looking at the table, he says, okay, the traffic is coming from 201.1, and this is basically the inside global address. And then the router knows that this is mapped to this private IP address on this device. So by keeping a map of the whole translation, when the packet goes out and the WAV packet comes in, the router knows this is for which PC on which port number. Now 10.10 colon colon 1556. This could be another application you're running on your desktop, right? So if that application, so when I say application, let's suppose I go on Firefox, or and then one tab is for YouTube, one tab is for my Yahoo. On one tab, I'm listening to watching something else. So I've got three tabs going on. So every single communication has port numbers on it. So that's what I'm saying. If it's 10.10, 1555 could be for something else. 1666 could be for something else. 1558 could be for some other applications which is trying to get to the internet. Every communication happens, it happens in the port number. And router is smart enough to know that this inside local address gets it gets changed to inside global address, and that inside global address is the one which basically goes on the internet. Because on the internet, all the ISPs they block basically the private IP addressing. And we saw earlier in the chapter that 10.0.0.8, 172.16.12, and 192.168.00 slash 16. So you got all these ranges which is blocked going on the internet. So that's why basically the NAT is used in order to make sure that your private IPs gets converted into the public IP. And this public IP will be going on the internet. So in the internet, obviously, they're going to be going to the 219.165. So, but this 219.165, this is for the facing for the internet, but inside they might have other servers basically mapped with a private IP address, right? So there is a device in there which is okay. I know what this server and IP address is mapped to. Did I answer your question, sir? Okay. Any other question?
Say, Imtiaz,
Yes, sir.
can you hear me?
Yeah, yes, sir. I can hear you.
Yeah. If you return to the what do you call it, PDF file, because here from inside global IP to outside global IP, you said it should be mapped IP address to other one, but these two IP addresses are not the same range, so it doesn't make any problems.
No, no, no. You're understanding. This 192.168.10.10 is your inside local private address, which gets
No, I'm
converted.
not talking about the inside. I'm talking about the inside global and outside global.
No, just let me explain this for a second. 192.168.10.10 gets converted to 209.165.200.226. Agreed? Yes.
Yes.
Now, this outside global, this could be your yahoo.com or YouTube or Gmail.
Mm.
Understood? Outside global is never inside. Look at this diagram. Outside is where your internet is. So anything on the internet has to have a public IP address. So that's what they're showing you here, outside global.
Yeah, I understand, but I mean, if the data should move from 209 and from the, I mean, let me say it like this. I mean, from inside global IP address, if you want to go outside global IP address, it should be sitting in the same range. Otherwise,
No,
you need
no,
to have kind of the routing.
no, absolutely not. This has got nothing to do with the ranges. All you're doing is taking a private IP and converting into a public IP. This is just doing a conversion. It's only doing a conversion. So that's what I said earlier. Look at this carefully. 192.168.10.10 changes to 209.165.200.226. Okay, fine. Now this is trying to go to this server, which is 209.165.201.1, right? Now, server has to reply back to this guy, right? So when the server traffic comes back in, he comes back in like this. He knows this is the IP address here because the server is only going to be talking to this 209.165. When the packet comes in here, R2 is smart enough. He knows that he has a table. This 209 gets converted to this IP address. Understood?
Well, actually, I disconnected, so perhaps I have to check it, recorded one later on.
Okay. Any other question? Nothing, guys? Okay. Thank you so much. Appreciate it. This was the last class. And so, if you have any issues, I told you guys, I sent you guys in last class my email address. You guys are more than welcome to send me an email if you have any questions or, anything like that. Okay.
Thank you,
Thank you so
Imtiaz.
much.
Thank you.
Thank you.
No problem. Thank you so much. Appreciate it.
Great. You have done a great session.
Thank you.